Hello, everyone. Thank you for joining us for our next session, Building an LLM Judge with Weights and Biases. My name's Anna. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for a presenter to answer live. Our session is being recorded. It will be available to view on demand within 24 to 48 hours on our Microsoft Reactor YouTube channel. With that, I'd love to turn it over to our presenter. Thank you for joining us.
Hello. And other interesting tooling. I find this topic really interesting because as an MLOps/ML person myself, I find that within the space of large language models, there's a lot of interesting ways that we can verify how well our LLM applications are doing. So before I get ahead of myself, let's jump in. But a quick background about me is I work currently at Weights and Biases, the AI first platform for tools to allow AI developers to build their models or utilize LM applications to its fullest capability. And so today we'll be looking at one of our tools called Weights and Biases Weave. If any of the topics I talk about in this presentation interest you, we are going to dive in deeper about evaluations around LM applications more in one of our upcoming courses. And so you'll be getting a nice early sneak peek at some of the resources that we're building out for you guys. But yeah, so let's jump right in and show you how you can go ahead and build effective LM judges for your LM applications. So I want to start off by saying LLMs are awesome. Personally, I use LLMs in way too many aspects of my own life. I use ChatGPT quite a lot. I use a lot of different tools when I do meetings to automatically transcribe and summarize notes. I even teach myself different topics using large language models. So there is a wealth of large language model tooling that exists in the world, either tools built on top of large language models, such as interesting search engines like Perplexity, or other interesting tools around how to actually build these types of effective applications. So the sky is essentially limitless when it comes to what you can actually build with a large language model. And a big reason why is that we're able to compose LLM operations together to create really powerful workflows that mimic what we'd expect software to do, but with a touch of underlying what feels like human reasoning. And so with that kind of in mind, there's also the inherent fear of failure around large language models. This is a common one you've probably seen a lot at this point, but there's a portion where Chevrolet used a large language model chatbot to go ahead and serve as the first line of defense for support queries. And so with the proper amount of jailbreaking on top of the LLM chatbot, a user was able to legally bind the chatbot to allow them to buy a car at a very cheap price. And so that is effectively what we're trying to prevent happen when we create these types of applications, especially if there are multiple layers that occur as you build something like a chatbot. It's not as simple as asking ChatGPT to go ahead and provide answers to questions. It's usually a lot of other software and other LM calls that happen behind the scenes. So like in this case, you can imagine that for Chevrolet, they had a collection of all of these different, essentially a database of common questions and answers to user inputs in the typical support world. But with the right way of formatting how you say things to a large language model, you can manipulate it. And that's where jailbreaking comes in. So how do you go ahead and mitigate these types of problems that occur in the world? Well, in the world of traditional software, where software runs and you know whether or not it fails immediately, aka it is deterministic, you can do so by using things such as CI/CD with unit tests, where you can go ahead and test the validity of each aspect of your code and then go ahead and actually read the code that exists to make fixes or build better, robust tests to ensure that your software tooling doesn't break or your software application doesn't break. But large language models suffer from a different problem. We do not have access to necessarily the internals of how these large language models operate. We shoved essentially the internet at an efficient algorithm and did a lot of proper processing to make it sound and feel like a human would. But in general, it is a next word predictor, and we don't know how it actually determines that next word outside of some interesting methods to kind of peek in that don't actually let us actually make changes on top of large language models. You can't go ahead and build internal tests inside of the black box that ChatGPT or other endpoints that you may be using create. And so we have a different set of ways to evaluate or understand how well these large language models operate. So the core of today's webinar is how do we build with LLMs and be confident to ship applications such that we can iteratively deploy it like we do with traditional software and ensure that we don't fall into the pitfalls that something like Chevrolet fell into earlier. And so there's a recipe for making this type of workflow work when deploying continuous LM applications that actually appropriately serve your business and your users jointly. So first, use experiment. Unfortunately, or for many of you who love the research world like I do, a lot of large language model application building is experimental by nature. Unlike software, where you know the end use case, with large language models, you typically learn how your users interact with your application by first releasing it to the world and investigating how they actually utilize that application. Maybe they're dropping in links, images, or asking really weird questions that at first you didn't expect, but actually make sense in the context of how your business operates and how a user wants your business to utilize large language models. So by tracking everything and experimenting and doing the natural scientific process of hypothesis testing and ensuring that you incrementally make changes to your application and understand its effect on how useful the change was for either the user or your business, this is that natural experimentation flow. And afterwards, once you do track everything, you actually go back and investigate individual examples. And this is where you might hear a term called annotation pop up quite a lot. This is that practice of inspecting each of these individual examples and ensuring that you actually grade them to how you as a human understand the ideal version of what the LLM should have said in that scenario. And we'll talk about two scenarios later today via code and also iterate more on one specific scenario in a future forward way. But like I said, I won't get ahead of myself. And then afterwards, we want to measure progress. This is the one that I'll talk about quite a lot. This idea of how do we effectively measure progress by utilizing a mixture of proper evaluation tooling. The one tooling that we will talk about, or technique, I guess is the most appropriate word, is building LLMs as a judge. But in general, by utilizing these 4 key steps of experimentation, tracking, inspection and annotation, and measuring progress, and using that in a nice data flywheel and feedback loop, you can go ahead and ensure that you ship LM applications that work the way as you intended so that your users are happy and your business is happy. Because let's be real, getting the GPUs to serve these LLMs or even using some of these endpoints can accrue quite a lot of cost if you don't do it in a very streamlined fashion. So let's talk about a hypothetical scenario. So in this case, let's do something like document information extraction. So in this case, what we want to do is pass a large PDF or a large markdown file filled with lots of interesting information, most of which is not useful. What we want to do is actually analyze the information in those documents and then aggregate some number that makes sense for us. So in this case, this could be a financial one where we want to understand for each of the different corporations mentioned in this document, what is the collection of shares that exist? Now, there's a lot of talk about calculations by large language models. So we're just going to ignore that for now and just say in our application, our large language model was able to calculate effectively. So we might write something like this code. It's as super straightforward. Use something like the Microsoft Azure OpenAI client to go ahead and serve your model, and then go ahead and utilize that using the SDK for OpenAI. So in this case, we use a served GPT-4 model, and then once you retrieve the response from this model, we parse it effectively using JSON because we told the large language model to use JSON. There's another key point about using the structured output mode, which I do highly recommend, but we'll omit that for this scenario and just assume that our large language model is able to spit out proper JSON. Next, we want to actually evaluate the performance of our application. So as you run each of these, this specific code of extraction over every data set point that you have, maybe in this case, you have pre-curated a list of what you believe are effective questions that hit the collection of questions that you imagine your user base to talk about. So in this case, we may be collecting hundreds of different PDFs or documents that have information about corporations, which we want to aggregate the share numbers about. And so you can imagine here, oh, this is a mistake, should not say translated page, but in this case, you can imagine this says the actual JSON that we wanted, the name of the corporation and the shares value. So in classical ML, you might just have one specific metric that you want to evaluate on. Did my model spit out the proper answer? So that's why in the world of classical ML, you may be used to just more standard accuracy measures, loss values, or F1 measures, something that really tightly couples to the task that you have at hand. And so that might look something like this, where this is one score that grades the overall quality of the response. Did we grab the name of the company, and was the share value proper? Aggregated together, if that JSON is fully correct, that is that one score that we have. But with foundational models, it's usually not that simple. And so in this specific scenario, it is actually can be considered as simple as that. But as we all know, real full-fledged LM applications aren't just one component. It's usually a collection of composed functions that all work together. So maybe 3 or 4 LLM calls all communicating with each other with other software components that pass and process the outputs of these models from one to another. So maybe you have one component that reads the document and creates a summary of the document itself, where it has all of the companies and maybe a mixture of all the values that make sense. Then we process that in an appropriate form using standard Python, TypeScript, whatever your package is. And then we pass it on to a second LLM that goes ahead and actually does the creation of the JSON, where it retrieves that name and gets that share score value. So out loud, those are 3 different steps, where each of those steps itself needs its own, it has its own inherent task, and therefore its own inherent metric. And so the LLM tasks all may vary and be composed together. You may be mixing together program execution with text categorization and translation. So you can go ahead and do really deep translation tasks, for instance. You can imagine that you can compose any one of these, all of these tasks together to create really complicated but interesting use cases that you all use here today. For instance, Perplexity, the search engine that does do a lot of LLM processing behind the scenes, is not as simple as search the web and pass to LLMs. It does a lot of work behind the scenes that actually make this something that's really useful to you as a user. And so always keeping that in the back of your mind of how you compose your application and how you want to verify each component of that composition is the core of LM evaluation. And so you can actually imagine scores look something like this, where it's actually a grid of different scoring measures, not always numbers, even in this case. Could be Boolean values, could be integers, floats, maybe even notes. But in this case, we're going to keep it simple. and do it as like a 1 through 4 scale, as you imagine, something like a Likert scale. And so you can imagine that this measure here, so let's hopefully this text tool works properly. This one is the overall score, as you can imagine here. Then this one might be something like the name score. Maybe you want to actually ensure that we always get the proper, fully processed name of the share values I want to capture. And this is the share match score. And so you can imagine there's actually a lot of ways to think about how this works. Maybe the share match score is actually the differential between the actual value and like that extracted value. So how far off were we? The name score might also have a component we want to see, did it get it close enough to the name we expected? If Happy Corp was the one in our ground truth answer, so our truest model answer, but our LLM returns something like Happy Co, how much should we penalize that? And lastly, looking at these two together, what is the overall composed score? So like I mentioned out loud, there's actually ways to look at each component of our output and associate an appropriate scoring metric around that. And so that requires its own tests. You can imagine that the name score, the share score, and the overall score all have this different mechanism to understand. So there's ways to do this. One, I actually think we should not forget. Oh, sorry, it's still in text mode. Let's go to box mode. As you can imagine, Python or any whatever programming language of choice you use for utilizing these LLM applications, in this case, I'll say Python, you use something like regex or if-else logic to go ahead and say whether or not it was true that something occurred. So like in this case, if you want to do something like exact match, you can literally say something like, does the share score equal the ground truth score? But when the situation gets more complex, maybe you want to add in some of this uncertainty inherently, then you can write very complex Python to build that score out, or you can use an LLM to actually go ahead and assess the quality of the output against the metric that you want that built-in uncertainty around. And we'll look at a specific example of this later. Not in this more basic share example, but something in a use case that I care more so about, which is about in the medical domain. But before I jump into that example, I'm going to throw a bunch of text at you, but don't worry, I'll go ahead and just explain this and leave this as a resource for you all. But in general, these are 4 requirements I agree with around what you need for proper evaluation. One is alignment. You want to ensure that each of these scores that you're generating actually match how you as a human would score it. So you can imagine that this grid there actually exists 2 grids in the world. And I'll update this slide in the future to show both forms. This score can actually represent all of the ground truth scores provided by a human who sat down and scored each of those 3 measures I talked about: overall score, name score, share score. Then you can imagine that these scores can also be the outputs of these tests that we just generated. So whether or not there was that match, or whether or not the LLM spat out a score that was within that range we mentioned. So alignment is this process of having our tests match the human expectation after a human sat down and wrote down what their answers are for those scores. So if those scores, the ones spit by our automated tests, don't match the manual process, that's a problem. That means our tests are not effectively capturing our business outcome that we took time to annotate over. And there are a lot of ways to actually create that score or generate or understand the degree of alignment. And I'll walk through that in the next few slides. Next is representation. So this is where standard data science actually comes into play. So when I talked about earlier, where you track everything in the user interaction between the LLM application you created and how it's utilized in your business, You want to ensure that after the fact, once you track all of that user interaction, you sit down and understand what classes of questions or use cases are your users actually using the LM application for? Are they using it in the way that you intended upon release? Or are they utilizing it in ways you didn't expect, but are still serving your business quite a lot of value? So once you understand those requirements, that's where representation comes into play. So when you use things such as sampling, weighting, and aggregation across the whole population of user interaction and paring it down to a set of data that actually represents all of your population itself, and then ensuring that the imbalance across that data set is also properly represented, that's when you have a good evaluation data set. And afterwards, this collection of systems and statistics is what actually drives the alignment and representation. So this is what actually allows you to go ahead and ensure that you can run evaluation. So are you spitting out the proper measurements that you want to capture across each of the different intended measures? So be it that overall score, name score, or share score. And do you actually have the tools in place to capture that measurement so you can create this alignment score? This is a bit complex out loud, especially with a bunch of text in front of you. But once I run through some code, I'm sure it will make sense. So LLM as a judge is a very simple concept. Human ratings, so a human sitting down with a nice UI where they click true or false or score an output through 1 through 5. For some of you who work in the enterprise world or most businesses, if you ever done a survey for your company, you may be used to these types of, or any survey in general, actually, you'll be used to this type of rating where you might say, I agree or disagree with a certain comment, or you might score something from 1 through 5. And I don't know about you, but I tend to take quite a lot of time with those. Tend to, especially due to a lot of the uncertainty about how I would like to score some of these answers, for instance. So LLM judges are a proxy to replace or aid the human in this process. So this is the process of having an LLM with a really good prompt that represents what we want a human evaluator to do as scoring. And so by doing this, you can run this not only quickly and automatically, but also do so in production. You can imagine as every new user query comes in, you have LM automatically score that output without having a human sit behind a screen and click those scoring measures yourself. And so there are a couple steps about how to do this. And so I'll run through them one by one. So one is first, you have to create a prompt or a prompt template that will be used to power this LLM as a judge. Note that these tend to be domain and task specific. So like in the case of our share example, we may have a prompt for an overall score, a prompt for the naming score, and a prompt for the sharing score. Then we curate that first training data set based on the real user interactions that we have, or by sitting down and creating a list of ideal questions that represent the core task our LM application is trying to solve. In this case, company name and share extraction. Then we want to verify the quality of the valuation. So running this through running our LM application through each of our data sets, through our whole data set, and then ensuring that we have humans annotate how well the output actually was. Then we sit down and have this feedback loop where we want to see whether or not the LLM judge that spat out an answer matched the human annotation. This is that alignment piece that I talked about. And then you rinse and repeat by replacing this LLM judge in your application, either offline or online, and then continue this iteration process. I'll skip this because I think we already talked about that. So now I want to talk about alignment, though. So I think the core piece about an effective LLM judge is that it aligns to your human annotation. If your LLM as a judge, I hear quite a lot in the space about how do I ensure that my LLM judge prompt does not get stale, and how can I ensure I iterate with the latest and greatest models to ensure my LLM judge is always the best form of itself, the best judge for my application, as the field changes quite rapidly, with new models being released and new workflows being released in the world of, for instance, like agentic judges or multi-agent judges, where you have a collection of LLMs all spit out scores, and then you create aggregate measure by either voting or by creating a sum, mean, or mode, or whatever aggregation metric score aggregation calculation that makes the most sense. And so alignment is the core piece that allows you to ensure that every iteration of your LLM judge is conditioned by a true human who sat down and actually graded those responses. So you do this by running through this great flowchart by Eugene Yan. I highly recommend reading his blog posts, as they talk quite a lot about these different topics, and he has quite a lot of surveys that run through the latest research about this. But first, you need to ask yourself, the task that I'm trying to solve, aka the extraction of the name and shares, is it objective or is it subjective? So, like, for instance, in this case, you can imagine subjective being closely related to something like content generation. Let's say you want to have a automatic summarizer for certain documents that match your stakeholder. You may want to have it so that your boss always gets over all of your business documents a nice summary that really aligns with their desired form of communication style. So in that case, that's really heavily reliant on tone or other subjective measures that represent that stakeholder, aka your boss. Or is it something objective? So whether or not, like in our situation, whether or not the JSON is correct. Was the name a one-to-one match? And was the share value a one-to-one match? Based on that objectivity versus subjectivity, you can then choose, let's walk through the objective branch first. You can choose more of a direct scoring measure. So in this case, can I simplify the task to be binary? Is it a yes or no? Did it match or not? Or if it cannot be simplified to a binary task, can I use I will use something like a 1 through 4 or 1 through 5 scale, where I have a really strong rubric that defines what constitutes a 1 versus a 2 versus a 3 versus a 4 versus a 5. And then afterwards, you can use more standard statistics techniques, such as Cohen's kappa or Spearman's rho, depending on whether or not it's a binary scale or a Likert scale, to actually calculate that alignment measure. So the way you would calculate it is by comparing this true or false from the LLM judge against the true or false from the human annotator, for instance. But actually, in our situation, we use a Likert scale, something from a 1 through 5 kind of situation. So we may use something like Spearman's rho instead. And regardless, these all relate to whether or not the output scores from the LLM as a judge or the tests that you generated for evaluation match the human evaluation itself. And then there's each of these calculations all differ by just some internal understanding of whether or not we take into account biases. For instance, like if a human evaluator tends to always choose things as true or false, or if LLM judge always guesses true or false, and then taking that into account on how taking that into account when creating the calculation of alignment itself. So not just looking at accuracy by weighing it by underlying biases, for instance. Now, on the other side, if we have something like a pairwise comparison, aka a human evaluator sat down and wrote the ideal summary that your boss would expect, and you want to compare it against the LLM's output itself, like does the summary of the LLM match the human written summary that you have in your evaluation data set, then you need to choose different measures to do this comparison itself. So in this case, you may want to use something like Cohen's kappa again to do a comparison against each like word position of the, you still want to use one of these scales necessarily to do this comparison. So Cohen's kappa is useful. But if you're really confident in ground truth, you can do something more standard like recall precision accuracy. But regardless of what final measure or I guess alignment calculation that is determined, you also need to determine whether or not do you want to use this as an evaluator or a guardrail. So the only difference between evaluator and guardrails is evaluators can happen offline. So things such as latency and speed, or latency, speed, and cost tend not to be a big issue in those situations. While guardrails care quite a lot about latency, throughput, and cost, as those um, tend to represent what you would want to do in real time as users utilize the application. So guardrails will spit out a score almost immediately after a user utilizes your application via by the LLM Judge itself, so you can automatically capture improper outputs. And this is particularly useful in applications that are quite sensitive, in which failure is not allowed as easily. So you can imagine this in domains such as the healthcare industry, where guardrails are quite useful. And also, certain measures tend to be more useful as guardrails. Hence, that's why you hear quite a lot of LLM judges that capture things such as hallucinations or toxicity, for instance. Those two tend to be really useful guardrails, as you don't want made up information or improper biased information to be released by your application. So let's go and run through an example. I won't actually run the code in this one. I'll run the code in the next one. But this is what you'll start to see in our new course that we're going to be releasing quite soon. So let's go and open the screen. So I'll zoom in here. Can I close this tree? Yes, quite nice. Let's see if I can make this a little easier to read. So what we're going to do is switch up the task from that boring name and share task that we had earlier, and we're going to do something a little bit more practical. So as you can imagine, quite a lot of time is spent by scribes to actually extract useful information from doctor's notes. So what we want to do is actually provide tooling to make the extraction of useful information from doctor-patient dialogue easier for these scribes. So in this case, what you can imagine is that we have this prompt here that says you are a medical data extraction AI assistant, and your task is to accurately extract and summarize key medical information from patient records. And so what we want to do is say, gather these specific elements from our patient doctor dialogue, and ensure that we don't have any inappropriate values. So don't have PII, use the patient, have bullet points, use NA if no values are missing, and keep it concise. So this is what you can imagine as a simple application. So something like our dialogue might be something crazy, like this unstructured text here. To make life a bit easier, I will go back to this slide here. Click this traces. We'll make it a bit easier to read. So if we go to the objects here, so what you see here is a Weave dashboard. I won't go too much in depth. I recommend trying our tooling out. This is our tooling for LLM operations. So be able to capture interactions from your LLM application, running evaluation, aggregating them to useful scoring dashboards, and also capturing data sets. So for instance, in our data set, you can imagine that our annotations, so our input, looks something like this. A bit hard to read also still here, I notice. So I do apologize. Well, I don't apologize. It's actually what an LLM is seeing too. So you can see that this is the dialogue between a patient and a doctor. So you can see that we have these limiters here, or I mean not limiters, but markers here that represent the doctor versus the patient interaction. So like saying something along the lines of, "Hey Dylan, what's going on? I lift quite a bit. I try to stay in shape as much as There's actually some weird processing here. In general, though, this is a back and forth between a doctor and a patient about a patient who has issues with their elbow, for instance. And so what you might expect is that you have a nice, simple LLM application here. So you call an LLM. In this case, we can use any model here. And then we'll actually run prediction here. And you can see here that the chief complaint is, if we look at the output itself, so we go to LM client predict. You can see that the output looks something like this. Let's render this in Markdown. The chief complaint, history, present illness, physical examination, symptoms, and new medications. And you can see that it actually matches what we told the LLM to extract from that information. So very useful for us to understand that, oh, visually, we can see that our LLM is doing a good job. So that's what we mean by track everything. So vibe checking is still a very useful resource when developing these LLM applications. But once we have done this on one example, naturally what we want to do is run this over a whole collection of data. So we might want to do is actually generate. Oh, is there a? There's no. The picture's not rendered here. That's fine. That's totally fine. So what you want to do is then use a nice UI and go ahead and actually annotate your data. So this annotation here represents the overall score and 3 key measures I care about with my task of summarizing doctor-patient dialogue into useful doctor's notes is word count, so whether or not it fell below 150 words, presence of the keys, so presence of the 5 different keys that we talked about, and then absence of PII, whether or not we ensure that we removed all identifying information from the summary itself, as these are more public information that we want to share. And maybe even a note about why we came to this scoring itself. So you guys can imagine these 4 numbers here represent all the different components I find important when doing this human annotation. And so after looking at our flowchart that we saw earlier, because this is still a factual objective task where we can simplify this to whether or not there was PII, whether or not the word count was below 150, and whether or not all 5 keys were present in the output from our large language model, we actually go ahead then and use something like Cohen's kappa or classification metric as our alignment score. We actually won't do that in this example here, but I want you to keep that in the back of your mind. As what we'll do is actually write different tests here. So, actually, I realized now I made a little mistake. Let's replace presence of keys within our mind with presence of bullet points for this demonstrative example. So what I might want to do is actually run some normal tests. So in here, I might have a test that says test adherence to bullet point format and test adherence to word limit. These 2 are written in standard Python. We can write assertions here that will return true or false whether or not the output from our large language model actually matches these 2 tests. Was there bullet points and was it less than 150 words? So that easily returns that binary true or false. At the same time, because the PII example is a bit more complex, we could use something like Microsoft's Presidio library to do PII detection. But in this case, we'll actually do something a little simpler. We're just going to write a large language model judge to do this instead. So what we'll do is we'll give a large collection of entities that our large language model will look for, and we'll actually tell it to look for this in the medical records itself, and actually tell it to return it in this format: the reason and whether or not it contains PII. So over here, you can go ahead and see that I can actually just use the LLM itself to go ahead and pass it the prompt that represents this. So in this case, analyze the text here, which is the output we see. And also, we have a very specific format we want this output to be, which is that contains PII and reason. Once we tell a large language model that information, we can just extract that score directly. So like in this case, does our output, so in this case, the output is this one here. Does this have PII? At spot check, you can see that calls the patient a 53-year-old male, which is, at least in this situation, not PII by our definition. We can go ahead and say true. This does, oh wait, sorry. Because, in our prompt, we actually tell it to, if there are specific ages, to mark this as something that has PII, for instance. Then we can see here that this actually does mention a 53-year-old male, which is something that we don't specifically want in our output. So in this case, we can see that this does, in fact, contains PII. So we mark that as true. So that is something that we can now use as an inherent feedback loop to say, oh, our judge caught something in our conception of what we're trying to remove from our output. So let's go and actually adjust our core underlying prompt of our task that we saw above here. So in this case, we might actually want to add in a requirement saying more details about what PII actually I want to remove, as we let, in this situation, the LLM decide what it considers as PII. So that's how you can see that natural interplay between LLM Judge conception and actually our task conception also. And we would also use a similar situation to create an overall score. So in this case, we call this a medical documentation quality assessor. Very interesting job title for someone to have, or LLM to have in the future. But in this case, we say, given all of the important requirements that we consider important as a human annotator, here is what we want you to do. We want you to return a score that is 0 or 1. We could also tell our LLM to return true or false. There was no specific reason for 0 or 1 in this situation. Just that's what we decided. But regardless, it operates the same as true or false. So afterwards, we can run this through, for instance, 5 examples and return this full evaluation dictionary here over all 5 of those examples. So if I were to go ahead and actually look at that evaluation, we can see by breaking apart each of those steps itself. So in here, we can see for each test what those outputs were. So in this case, for this one specific example, where the example is this was the input transcript, and this was the output summary, we can see the scoring for each of these. That's just to say that we want to ensure that we can easily understand where any mistakes occur in our evaluation pipeline itself, in both either the manual tests or the LLM tests, where behind the scenes it may have a complex dictionary of fields that you want to analyze in this situation. So like in this case, the text mentions the patient's age, which is considered PII, for instance. However, this is a bit hard to look at itself. You can see here that we also have the values here alongside with true counts and fractions. But at least for me, I like nice little dashboards. So sorry, that's a bit weird. So what I want to do is actually visualize this in much more understandable radar plots or bar plots. And what's nice about this is as you iterate on different variations of judges and evaluations, you usually go ahead, and I'm not sure if this will actually work, but we'll see. You can actually make comparisons, for instance, between each of these different judges that you try out or different models that you try out. So like in this case, if our definition of scoring changes, we can actually investigate its effect on the final score itself, or even go down and see example by example what was marked as true or not, for instance. And so ensuring that you have proper dashboards to investigate the impact of changes from your evaluation dataset over the different evaluation metrics that you want to test out, or even adjusting the metrics themselves to understand the effect on the supposed quality of the outputs of our model, are all really important to aggregate. And so let's actually go and iterate on LLM Judge specifically. So I'm going to go and run through this notebook here. So hide the sidebar. This is a nice little Visual Studio example here. So this situation, let's change from the medical use case. And let's actually look at alignment, because in the last one, we didn't look at alignment specifically. So in this specific task, what we're trying to do is convert a query into an essay. So build an essay based on some information and maybe a prompt about what that final essay should be about. So like in this case, you may have this very basic one where you say you're an expert essay evaluator. Please evaluate the following essay according to the holistic rating for source-based writing rubric on a scale of 1 through 6. So in this case, this is a very simple prompt here. So we have an evaluation data set that I will show you now. So let's go ahead and go back here. Let's go to the next slide. Evaluation. Oh, this is the leaderboard. Sorry about that. Should have probably pre-rendered this beforehand. Here we go. So if you want to go and look at the data set itself, you can see that we have this full text about what we may want to create an essay about, or what the final essay should look like, and then our human annotation score here. So what we want to do is just ensure that we write essays of similar quality given the same prompt that generated this style of essay. And so if we go back to, let's also move this here. So that's what our data set looks like. So what we want to do is ensure that for LLM, which will go ahead and generate an essay based on the text that we provide to it, we want to ensure that the score, in this case, the text was the one that's already pre-generated from an LLM, and we had a human annotation score. Now we're trying to create an ideal judge in which the score from the judge matches the score from our human annotations. So we can have this really simple way of checking whether or not the LLM judge score and the human judge score match. So this is by the exact match. Do they exactly equal each other? So after looking at that, we can see that once we do this, we can see that not a single LLM judge score matched the score from the human annotation. That's really bad. That means we had no alignment between our human annotators and that judge prompt I just showed you earlier. And that judge prompt, as you can see here, is this very simple one here. So instead, what we might want to do is actually start to make adjustments on top of this. So the first change we want to make is maybe actually turn this into JSON mode. So go ahead and ensure that we parse the output from our LLM in a form that is JSON serializable, and then we can actually go and parse that to actually get that score. Because if we were to actually go and jump into this here and see the output of our essay evaluator, you can see that all of them failed because actually failed to parse JSON, because the output of our model was in JSON, as you see here. So even though the score said 2, and this may have matched what we expected from the human annotator, it never even got there in the first place. So the first gotcha is ensuring that the output of the judges you create are parsable by design. So this is where we start to use that JSON handling mode. So now when we rerun this situation, it's a bit better. We can see now that we actually have scores. On average, our LLM Judge persists 2 by 2.2 for all the scores that were generated for each of the examples. And but the thing is, only 2 of them exactly matched. And so if we wanted to go in, we can probably isolate the specific examples that failed or did not fail. So in this case, this one gave a proper score. The score in this one also gave a proper score. And you start to see all of them are pretty much giving 2s across the board. So we can see here, this is one of the issues that we're facing. Oh, we see 1, 3, yeah, another 2, and a 3. So it's living within that 2 to 3 range. So it tends to be biased towards 2 or 3. And a big part of that is we didn't actually give a proper rubric to the judge itself. So The next thing we have, so actually one more step, I got a bit ahead of myself. One thing we can also do is, instead of just saying, hey, parse this JSON, most modern foundational model providers allow you to use typing or structured outputs to spit out a form that is always going to be an appropriate JSON form. So by using the system where we have score and reason be the judgment, we can pass the schema over and return that response. The OpenAI endpoint is really good at doing that. We still see that we have this mean of 2.3. And I'll save you the trouble and say that that issue of staying between 2 and 3 is the problem of our current prompt still. So what we want to first do is verify whether or not our alignment makes sense, though. Like maybe all of our human evaluators are also giving 2s and 3s. At a very spot glance at this, you can see that this is untrue. You see 1, 4, 1, 3, 2. Well, all our predicted scores are 2 here. And the way to verify this is we actually want to also calculate Cohen's kappa. So like I mentioned earlier, this is a way of just ensuring that we find the match between the human evaluator scores and our predicted score, but also weight it based on our bias towards scoring against a specific score itself. So in this case, our LM judge always skews towards the score of 2. So Cohen's kappa takes that into account in this alignment calculation, something that's a bit different from just doing exact match, for instance. And so after calculating Cohen's kappa, we see that we only have this alignment of 0.189. So that's not very good. So our next natural step is, earlier we alluded to the holistic rating for source-based writing rubric as the rubric that the LLM should use. What we're going to actually do is write that rubric out directly to the LLM and see how that may affect the output of the model. So with that being our next step, we can still use the same code that we showed earlier, just swapping out the prompt here and rerunning. We can see that now our score is a bit higher. It tends to be 2.8 on average. And now we have 4 exact matches. So that's looking a lot better. So now we're jumped from 20% accuracy to 40% accuracy by simply writing the rubric explicitly. And that also increased our Cohen's kappa to 0.366. If we were to go through the examples themselves, you would see that 1s and 4s tend to pop up a bit more now. So the next example we want to do then is to actually drop in a couple few shot examples. So like in this situation, we want to ensure that we have all of the different scorings mentioned here. So example of 2, 4, 5, and 1, for instance, for provided essay. So by providing some few shot examples, so examples of ideal outputs with the appropriate score and reason to condition our prompt, we actually see that there is yet another increase in the output of our model. So we can see here that the mean is now around 3.0. We can see that the exact match is still only 40%, unfortunately. However, our Cohen's kappa jumps up from that 0.39 to 0.521. So that inherently means that despite our true accuracy still not being increased in this situation, overall, the skew and bias of our LLM judge towards a particular set of scores was reduced, which is something that we want to always have happen when we do our LLM judge scoring. We want to ensure that our scores tend to match what we expect from the human evaluation, including any skewing that the human evaluators also have on their end. So even aligning the underlying quote-unquote biases from our human annotators is something that Cohen kappa also allows you to investigate in this scenario. And so there's more rules that we can take into account when building out stronger LLM judges, but structured outputs, explicit rubrics, and few shot examples are 3 really useful ones. And once it gets to a point where you have a really good set of all of these prompts and outputs from your LLM judges that are properly aligned against humans, you gotta go ahead and fine tune or train your own reward model that represents this judge that you created to kind of use this in a more effective guardrail sense, as opposed to hitting the LM foundational model endpoint and using those sweet token costs. But in the future, you can imagine that as the LM judges changes and your specific criteria of your LM application also evolves as you make more complex things, complex functionality of your LM usage, you want to start to think about how you can scale even the creation and alignment over these LLM judges that you want to generate. So an interesting approach is called eval forge or eval gen, which is a concept of, let's say we love using LLMs everywhere, using an LLM that looks out the outputs of your model and the alignment annotations from your human annotators to dynamically generate LLM judges and Python unit tests for you. So you can automatically create LLM judges that grow with your application as you make changes. A bit future forward and has a lot of failure points themselves. But as you can, the core idea here is that one LM judge will not solve it all. You need to diversify the tests that you create, both from a Pythonic sense or unit test sense way, and the LM judges you create to capture all aspects of your LM application task itself, especially as it becomes more complicated. That's it. Hopefully, that was a very interesting understanding of the evaluation landscape and also how LM judges can be iterated upon alongside alignment metrics to really ensure that you capture the human expectation of what ideal outputs look like for your LM, and also ensure that you can automate part of that process. And so now I'm going to see if there's any questions real quickly. And if not, I'll flash a dashboard of our own implementation around this eval gen itself. So I'll go to the screen here. Cool. Looks like there's, feel free to ask any questions if you'd like. If not, I'll flash one final screen here. Oh, I heard my voice by accident. If not, I'll flash this one final thing as some interesting research that's being made. You can imagine that you want to dynamically generate LLM judges yourself. So in this case, you can imagine that you have this really complex set of criteria that you might want your LLM judge to create. Is this forge test? This is eval gen test. Which one is it? Let's do forge test. Yeah. Nope. This is eval gen test. So in this case, for instance, I have that same medical use case I showed you earlier. Oof. We love when live demos get a little bit of a snag here and there, but no worries. Okay, we'll go to code. It's a bit easier in this situation. You can imagine that there's this complex pipeline here that I won't bore you with, for instance. But you can see that everything we said out loud is essentially something that can be slightly automated with the help of LLMs. So understanding what tasks we want to solve, understanding what core human annotation-based criteria we want to actually investigate, be it word count, absence of PII, or bullet point adherence. And then afterwards, what we want to do is actually create assertions. So go ahead and looking at our understanding of, hey, we want to ensure that we capture any PII that exists, we can actually generate tests dynamically. So those tests can look something like this. Does our test can be something like a unit test here, or it can be something like an LLM prompt. And both of these were automatically generated by a complex LLM system that was able to auto-analyze a lot of different components by a really well-curated evaluation data set. And so this LLM judge could definitely be increased in terms of quality by adding in a much stricter rubric and much stricter few-shot examples. So that's what you'd imagine the next iterations on top of this would be. But that's just to say that in the future, you can imagine that not only are we automating the process of creating of scoring criteria that align with human expectations, we're also automating the scaling out of the generation of this type of tooling. And this is really exciting and useful, as at any point your LLM application evolves, you also have that a guarantee around the scoring of that LLM application to also grow as that application grows. So that's just to say, I want to thank you all for coming to this presentation. Let us know if there's any other additional information, and feel free to, feel free to look at our new course coming out about evals, in which we'll dive in deeper around this information. Happy building all.